All right, so billiard balls colliding is a classic situation. It's in every physics textbook that deals with momentum. So we'll deal with this question here. Before the collision, we have just one ball moving, and it's moving to the east at 3 meters per second. I'll call that ball A. So the velocity of ball A is 3 meters per second, and it's east. My arrow to the right will represent east. I'm also going to call it the x direction, and I'll call north the y direction. The second ball starts at rest, so 0 meters per second. Okay, so that's before the collision. And now after the collision, we're going to have the two balls moving. We're going to have one ball moving at, I'm going to draw the one going at east 60 degrees north. So what I'll do is I'll draw components in here. 60 degrees. And I'll label the hypotenuse. I'll call this ball A, VA prime. It's unknown. I don't know what the value is. And I'm going to label these components now. So the horizontal component, I'll call this VA prime X, and then VA prime Y. Secondly, the other ball, which is of equal mass, that's important. All of these have the same mass. It moves at 30 degrees, east 30 degrees south. So I'll label this velocity as VB prime, and then I'll draw in components for that. So I'll have a VB prime in the x direction and a VB prime in the y direction. Okay, so what's going to happen is momentum is going to be conserved, and it's going to be conserved in both directions. So now I organize my solution into two columns. I'll say the y direction and the x direction. I chose the y direction first because it's a little bit less complicated, but just a little bit less complicated. The conservation of momentum applies to each dimension. So the total momentum in the y direction before the collision has to equal to the total momentum in the y direction after the collision. And for the y direction, we're a little bit lucky that it starts off with no momentum, 0 Naru's in the y direction, because we just had one ball moving and it was moving east, perfectly east. So there was no motion north or south. The momentum after the collision in the y direction, well, the two balls are going kind of in opposite directions. One's partially north, one's partially south. So they need to add up to 0 though, because that was the initial momentum. So I'll highlight them here. This momentum and this momentum, they actually have to cancel each other out and make 0. So what I'll first do is I'll say that 0 has to equal ball A's, I forgot the mass there. Momentum is mass times velocity, so mass times ball A velocity in the y direction. And that's ball A is going north, so it's in the positive y direction. Now ball B is going south, so I stick a negative sign there because it's in the negative y hat direction. They're equal masses. Those two m's are going to cancel out. So essentially what happens, let me cancel some stuff out here. M's cancel out. I can even cancel out these y hats. And essentially, the one equals the other. So that's the y directions equation. Kind of complicated. It's not even done yet. We have to deal with trigonometry SOHCAHTOA because these are components as well. But, I'm going to come back to it. I want to work a little bit on the x direction, which I need a bit more room for. Okay, in the x direction, same thing. The starting momentum in the x direction has to equal the ending momentum in the x direction. Now we do have starting momentum this time in the x direction. Ball A is moving, so its momentum is going to be mass times, mass times 3. 3 is its velocity. So that's the starting momentum. The ending momentum in the x direction, it's going to be the x components of the two balls added together. So it's going to be mass times the VA x prime. So that's ball A's x momentum, and then ball B's x momentum will be mass times velocity of ball B in the x direction. There's a mass in every term, so they cancel out. Okay, so 3 equals okay, so that's our x equation. So we have two equations, and right now it looks like there's 4 unknowns. So what we're going to do actually is relate some of these together using SOHCAHTOA. So I'll go back to the y side now and look at SOHCAHTOA. So VB, this one here, VB prime y, that's going to be VB prime times sine of 30 degrees with SOHCAHTOA. And similarly, VA prime y, so this one here, that's going to be VA prime sine of 60 degrees. Now I move back to the x side. Okay, so 3.0 equals VAX prime. So that's this one right here. That's going to be VA prime cosine 60. And then VBX prime, this last one right here, that's going to be VB prime cosine of 30 degrees. It gets quite messy. However, now we're at the stage where we have just two unknowns, VB prime, VA prime. VA prime, VB prime. Two unknowns, and we have two equations. It should be solvable, actually. Yeah, that should be solvable. We can do substitution, try to solve it out. What I'm going to do is I'm going to type these into Wolfram Alpha. Okay, so I'll say out loud when I'm typing. So I'm not going to really type VB prime and VA prime. So I'm just going to use, I'll just say B and A actually. So I'll say B times sine bracket 30, close the bracket, equals A times sine bracket 60, close the bracket. And then I'm going to type the word and, A-N-D. To communicate to Wolfram Alpha, I have a second equation coming up. And now I'm going to type 3.0 equals A times cos bracket 60, and then plus B times cos bracket 30. Okay, that looks good. I'll hit enter. It'll show me, it'll show me what I wrote in, so I can check to see if that's what I actually wanted. And it looks good, and it's telling me what A and B are. Okay, it's telling me what A and B are. So it's telling me that A equals 1.5, and B equals 2.6. All right, so those are the speeds. Those are the magnitudes. They gave us the two angles, and they asked us to find the two speeds.